Okay, in this session, we are going to discuss about reaction intermediates. Actually, this reaction intermediates are most important topic in organic chemistry in the beginning. There's a great majority of organic reactions, actually, they are said to be multi-step processes. Actually, they are involving intermediates whose lifetime is usually very short, about 10 power minus 6 seconds to a few seconds will be there. So an understanding of structures and properties of these intermediates are normal covalent compounds is important. So they may be ions or they may be radicals is of paramount importance to understanding organic reaction mechanism also. As we shall see the energy profile diagrams, intermediates sufficiently possess sufficiently low energy to be formed under reaction conditions. But in most of the cases are not stable enough to permit isolation. That means intermediates are not stable to be isolated. So this is especially true for these intermediates in which carbon has fewer than 4 covalent bonds. A brief description of some kinds of intermediates we will see in this session. Not only that one, what is the reason behind studying reaction intermediates is that the majority of the organic reactions occur because of these intermediates, and these intermediates are detected by methods called spectroscopic methods and are trapped chemically, and their presence is confirmed by indirect evidence. On the other hand, synthetic intermediates are stable products which are prepared, isolated and purified and subsequently used as starting materials in synthetic sequence. So, in keeping these points in view, we will start discussing about the major important and the most common organic reaction intermediates. In the first case, we will say they are carbocations. Carbocations or carbocations. Here, earlier we saw in the homolytic, heterolytic cleavages, there are some intermediates are said to be generated during the separation of a bond. Now we are saying this intermediate is carbocation. So carbocations are said to be the key intermediates in several reactions, particularly nucleophilic substitution reactions as well as electrophilic addition reactions. These carbocation intermediates are important. Earlier, actually, we used to call these carbocations carbonium ions. What is the earlier information about these carbocations is called as carbonium ions. Carbonium ions. Okay. Now, what is carbocations? Carbocations are key intermediates of reactions, particularly nucleophilic substitution reactions as well as the electrophilic addition reactions. Okay. As you know, these are obtained from heterolytic cleavage. we will see their structure first. We will see their structure. Actually, in studying the structure of carbocations, as if you know that carbon is positively charged. Around the carbon, there are 3 bonds are there, and this carbon is positively charged as one p orbital, which is present. Is actually this is an empty orbital, empty p orbital, and this carbon is positively charged. We have 3 groups are there. Assume capital R is the symbol, and there are sigma bonds are there. 3 sigma bonds, and we are going to see the bond angle in this one is 120 degrees. 120 degrees. And whereas this carbon is there in the carbocation, this carbon is there, that is said to be sp2 hybridized, as we have discussed in the previous session also. That means generally what is carbocation? Carbocations are positively charged carbon atoms and bonded to 3 other atoms or groups. Has no non-bonding electrons. So here this orbital is empty, that's why. It is sp2 hybridized. Yeah, carbocation is what kind of hybridization? sp2 hybridized. And the structure is a planar structure. Here, what is the structure here? That is for carbocation is planar structure. As you know, this is sp2 hybridized planar structure. And bond angles are about 120 degrees are there. And we have one vacant p orbital. Vacant empty orbital is nothing but vacant unhybridized p orbital, that is associated with the carbon only, right? And this is in the case of CH3 plus lies perpendicular to the plane of CH bonds. So what is this one? This one is lying perpendicular to the plane of CH bonds. CH bonds, so carbon and hydrogen bonds. In the case of methyl carbocation, this is identified. So this is regarding the structure of carbocation. So that means orbital picture of carbocation we just now saw, and this orbital picture is giving this information. This is nothing but orbital picture of carbocation. Okay. And we must know how it will get generated also. Okay. And its stability also we will check it off. Formation, how it takes place. Formation. So carbocations can be generated in variety of ways. Some of reactions in which carbocations are formed, we will see. One we will call it as solvolysis. Solvolysis. Solvolysis of CX bond where we know that X is nothing but halogen. That may be or OBS, etc. Particularly halogens. Okay. In this, if you write that Rx, that gives R plus plus X minus. So this Rx gives rise to R plus plus X minus. This R plus is carbocation. And the second one, the deamination of amines by nitrous acid. Deamination of amines by nitrous acid. So we will see what is the deamination means. In aniline amines, nitrogen with hydrogen also present. We have an alkyl group assume or NH2 is there. Suppose in this or NH2 is there. In the presence of this HNO2 nitrous acid, it will become R N2 plus, and further it will become R plus plus N2. That is called as deamination. So nitrogen hydrogen bonds separated out, nitrogen gas came, finally R plus obtained. That is the another, this is one case. Another case is there that we will call it as protonation of alcohols. Protonation of alcohols followed by dehydration. Followed by dehydration. We'll see alcohols are nothing but ROH, general formula. If these alcohols in the presence of acids undergoes protonation, gives ROH2 where oxygen will get proton positive charge. And this upon dehydration means loss of water, this R will become positive, carbocation. So likewise, several kinds of things are possible in the organic chemistry. That means not only one method, we have shown a few methods regarding the development of carbocation. So that means carbocations can be generated in a variety of ways. Of some of the reactions we have observed solvolysis of CX bond, deamination of amines by nitrous acid, protonation of alcohols followed by dehydration. So the three methods we have shown. In these three ways, we can say carbocation can be developed, generated. And now we will see some things related to their stability also. Stability. Stability of carbocations. As we have known that the increase in the stability of carbocations with the addition of alkyl substitutions. That means in carbocation, if we have additionally added some alkyl groups to the carbon, which is called as carbocation, then what will happen? Definitely the stability increases. So there is a strong evidence is there, the both physical and chemical, that alkyl groups are more electron donating than hydrogen. So physical evidences are there, chemical evidences are there. They are telling that the alkyl groups are there, right? These alkyl groups are more electron donating than the species what we call as hydrogen, because methyl carbocation, if you take in that, hydrogens will be there along with carbon. In a place of that hydrogens, if you put the alkyl groups, then you can easily enhance the stability of the carbocation. That is the meaning of it. That is evidence also from the experiments noticed. That means it is therefore the follows, when these groups are attached to the electron deficient carbon, then they tend to increase the uh, release the electrons and partially compensate the electron deficiency of the positive carbon. Automatically what happens, the positive charge gets dispersed over all alkyl groups, and this dispersal charge increases the stability of the whole system. So accordingly what happens, tertiary carbocations are said to be more stable than secondary ones, which in turn are stabler than primary carbocations. So that is we will see here 3 alkyl groups. If you attach to this a carbocation carbon, this is more stable than the secondary one. If you write the 2 alkyl groups, as these alkyl groups increases the stability of the carbon, positive carbon, this is secondary. And as you see the primary, we have only one alkyl group is there. Okay, here assuming this R is nothing but alkyl group, which increases stability of this primary is more than that of the methyl carbocation. Right. So what is this one? This one is the first one is tertiary. The second one is secondary. This is primary. This one is methyl. This is what we have discussed in the previous session also regarding the carbocation. So greater the stability of the carbocation is coming when it is said to be alkyl substituted carbocation. And this phenomena is ascribed to the phenomena of hyperconjugation. In the next classes I will discuss what is the reason behind that one. According to this one, there is a information which is noticed also, carbocation stability. The stability of the carbocations is because of this hyperconjugation information also we have. So that I will show you briefly, and again I will discuss in detail in the hyperconjugation. So let us see a thing related to alkyl substituted carbocations. The question is nothing but alkyl substituted carbocation. They are stable. What is the reason? Due to the point is nothing but hyperconjugation. Hyperconjugation. Actually, this is also known as no bond resonance. If you take a structure like this, I will show you. This is hydrogen. Here also I am taking hydrogen, and it's linked with CH2. plus carbocation is linked with an alkyl group. That means the entire portion here I have shown is an alkyl group. With this carbocation, it gives a resonance. That is no bond resonance. I will show that with one of the hydrogens of this alkyl group, I will completely leave the bond. I won't write any bond, but I will shift that bond towards this carbocation and makes this double bond between the carbon atoms. Like this. At that time, hydrogen becomes positive proton. And this obtained when we have separated carbon and hydrogen in alkyl group. So no bond is there between this carbon and hydrogen. So where no bond is there, so here we don't have any kind of bond. No bond. But we could able to write the resonance that is called as no bond resonance, which is also known as hyperconjugation. Now, I'd like to continue this one by keeping, I want to make this first hydrogen as stable. Then again I have to connect that hydrogen with carbon by leaving another hydrogen and making this is H plus. Here also we have shown no bond is here. So there is a double bond with carbon hydrogen. So again I can write for third hydrogen like this. Here I am keeping this third hydrogen as H plus. That means this is in the case of a primary carbocation I have written. So this is I have written for primary carbocation. That is for a secondary carbocation. Such kind of things more can be written. For one methyl group we are writing 3 structures. If we have 2 methyl groups in the secondary carbocation, we can write 6 structures. If we have 3 are there, we can write 9 structures. So that means in a case of secondary we will get 6. In a case of primary we got 3. Secondary we can get 6. Tertiary we can get 9. Okay. So that one I will say that similarly what we can write it as, if you take the secondary carbocation like this, secondary carbocation, this one will give 3 plus another one here. This we will get 3. A total of how many we will get? 6 we will get when you have taken the secondary thing. Similarly, if you take tertiary, means 3 such type of things are there. Hyperconjugative structures you can write total of 9. For this you can write total 9 no bond resonance structures you can write. So you can write it off. That means secondary carbocation more equivalent structures can be written than for a primary carbocation, whereas still greater number of such structures can be written for tertiary carbocation. So here resonance plays an important role, I can say, the factor that will enhances the stability of carbocation. So what is playing an important role here is nothing but resonance. So here resonance will enhances I can say enhances the stability of carbocations by the delocalization. So this is what happened here. We observed is a delocalization of its charge. By the delocalization of its charge in systems like we have already told allyl and benzyl carbocations also. Allyl and benzyl carbocations. So this is regarding allyl. If you take allyl, I'll show you allyl how it is there. That is CH2 double bond CH2 plus is there, and its resonance structure will be CH2 plus single bond CH double bond CH2. This is for allyl. Whereas we have observed the benzyl also in the same way. Benzyl. So this is benzyl. I can say this is benzyl. So this can give positive charge at on the benzene ring. That means carbocations will be developed. So whenever we wrote like this, that positive charge developed. And here next to this one only develops, it will be distributed like this. Even you can write one more. By keeping like this. So here what you observe is nothing but there is stability is attributed to these carbocations, allyl carbocation, benzyl carbocation, because of resonance, that is delocalization of its charge in systems like allyl and benzyl carbocations. Not only that one, when you are going to talk about a few things related to some particular special examples, the carbocation stability can be understood in the same manner. That is of things called as phenyl groups are there in place of alkyl groups with the carbocation. Then how it will be there? We'll check it off. Now we are going to see triphenyl carbocation. So in this triphenyl carbocation, as I said earlier, which is more stable, and this is actually obtained in a liquid sulfur dioxide. Let us see how its equation is there. It is C6H5, phenyl means CH5 group, and here also we have C6H5 group. Here one halogen is there. Actually it is a triphenyl methyl bromide is there in liquid sulfur dioxide. In liquid sulfur dioxide, it forms a carbocation that we are calling as triphenyl carbocation. This is and Br is because of electronegativity, it is moving with the electrons, pair of electrons becomes bromide. And a solvent with the carbocation does not react actually. So what happens? It is possible to determine its quantitative by measuring electrical conductivity of the solution. Actually, triphenyl carbocation is stable. That when triphenyl methyl bromide is placed in liquid sulfur dioxide, then it is possible to determine its quantitatively and measuring the electric conductivity of the solution. Okay. And this kind of triphenyl carbocation, if you consider, in this case, if you take one ring of it, that means one phenyl ring, if you take like this, you can write like this. Rest of the two phenyl you will write pH only symbol, pH2, right? So then what happens? You can write the resonance structures, and then that ring will get the positive charge, ring will get the positive charge, like this. We have a positive charge is developed in the ring. Double bond with the CpH2 is developed, and that can be written with this extension. Then you can write positive charge in other side. So here you can write positive charge. Even you can also write one more. That is okay. So what we have noticed here is nothing but in this triphenyl carbocation, because of the steric effects and their discussion, came into a key role in the ease of formation of stability of the carbocations also. Actually, they are derived from highly substituted substrates. So, the stability of such carbocations is attributed to the steric relief, and that is also should be discussed. So, this is one example I am telling, the triphenyl carbocation. I will give you the reason behind that one also, how they have given in the NCRT we have, I'll show you. So the same thing here, the question here on this thing here given in the exam, the NCRT we have, what is the question related to this one is, the structure of triphenyl carbocation given here, and is very stable with salts stored for months. What is the region with high stability of a carbocation? The question in NCERT given is the structure of triphenyl methyl carbocation. Triphenyl methyl carbocation is given below. So what they are given is, I will give you the same. This is the structure they have given. Triphenyl carbocation, triphenyl methyl carbocation. Okay. And this is very stable. They are telling this is very stable. This is very stable, and some of its salts can be stored for months. And they ask the question, explain the cause of high stability of this cation. So this is the question in NCRT they are given. So we saw that this is a triphenyl methyl cation, whatever is there, that is due to resonance only. The positive charge can move at both the ortho and para positions. So we have shown the ortho position, we have shown the para position in the above examples. And for one ring we have to given this type of three structures. Like that, if you use three rings, then you will get 9 resonance structures of it. So that kind of resonance is making this carbocation more stable. Okay. So this is one question which they have asked in NCRT. Similarly, we have one more question is there. We will see in NCRT what the question they have asked is, which are the following ions is more stable? Use resonance to explain your answer. They are asking, they are telling, use resonance to explain your answer. So here they are given two things here that I will write it now. Two things. Ring they are given, a double bond inside it attached to that one positive carbon, CH2. And another one given, B. In that there is a double bond, CH2, positive charge. This they are calling as B. Now if you observe both these, we will usually vote for more stability for A. A is more stable in this case. And also it is actually more planar because of hydrogen atoms are there in this one, and which is stabilized by resonance also. As if you write this resonance of this one, you can comfortably write the resonance of it to make the second one. So you are observing the same thing. In this, carbocation B, whatever is there, is non-planar, which does not undergo any kind of resonance. So what is this B? B is non-planar, and it does not undergo resonance. So further, what is the point here is the double bond is there, is more stable within the ring in comparison with the double bond outside the ring. So in the case of B, the double bond is outside the ring is there. And in the case of A, the double bond is there inside the ring. So because of this one, the stability also can be understood. So double bond inside the ring is stable, then the double bond outside the ring. So carbocation, carbon, if it is positive on the benzene ring, that is not stable. Carbon attached to the cyclohexane ring, which is stable compared to this one, because cyclohexane we have a double bond inside it. That is a simple thing, but it is crucial one. It is most crucial one under our discussion. And further, also we will see some interesting things in this carbocations. Here, what is the reason behind that stability of the carbocations we have just now observed? In the case of the benzyl and other things also we observe. Now, the special stability, nothing but special stability factor to these compounds, particularly because of conjugation inside that structure. Even more stable ions are developing in this one because of vacant p orbital in the carbon. So the bent orbitals of any kind of ring structure is there. Ring structure, vacant p orbitals of these carbon atoms will undergo any kind of delocalization. So here bent orbitals of some cyclopropyl rings are there, and the vacant p orbitals of cationic carbon is there. That is making it stable. So the carbocations are planar and shown by fact that they are difficult. It is impossible to form a bridge heads where they are not be planar. So at bridgeheads here, like we have shown here one ring here. At bridgehead, if they are present, they are not said to be stable. So it is difficult, it is impossible to form carbocation at bridgehead. So here what we have mentioned is very clear. So stability of carbocations, till now we have explained using hyperconjugation, and in some cases we have vinyl carbocations are also there. Vinyl carbocations, they are also stable because of no stability, no resonance. But vinyl carbocations are there. Resonance stability lacks completely, therefore they are much less stable. So here what we have discussed is the special stability of cyclopropyl methyl cations. Cyclopropyl methyl cations. Cyclopropyl methyl cations. Cyclopropyl methyl cations means as know that this kind of structure will come. Cyclopropyl ring you can attach to this. These are more stable than even benzyl cations also. So the special stability of this kind of cyclopropyl methyl cations, result of conjugation between the bent orbitals of cyclopropyl ring. Here this is cyclopropyl ring is there. They have bent orbitals will be there, and because of angle strain and vacant p orbitals of the cation carbon. So this carbon is there, that is having vacant p orbital we know, and there is a conjugation takes place between the empty p orbital of positive carbon and the bent p orbitals conjugation. Okay, so what will happen? These carbocations are planar, shown by the fact they are difficult or impossible to form bridgeheads. So here this at bridgehead, so this is the point, I can say bridgehead at this. It is difficult, so bridgehead means it is difficult where they are not planar. So here what we observed is nothing but carbocations are planar, shown by the fact these are difficult or impossible to form at bridgeheads where they are not planar. So at bridgeheads they won't form. So that's why what happens, these rings makes the compound stable. So stability order of carbocations is explained by hyperconjugation only. Now what is the stability order? Stability, I'll give you stability. Stability is directly proportional to hyperconjugated structures. Hyperconjugated, and more is the hyperconjugated structures or number of alpha hydrogens. Number of alpha hydrogens. So these alpha hydrogens are associated with alkyl groups. That's why we are always telling they are stable. There are some examples also there to understand this one. Okay, Now we will see one more example. Triisopropyl chloride. Triisopropyl chloride. Actually, three isopropyl groups are there in this one. That I will write it with a carbon here. Here carbon is there. It is having two methyl groups, hydrogen, and this carbon is positive. Another one is there, CH. We have CH3, and one more is there. I'll write here, CH. This carbocation is plus here. So here what is happening here is nothing but in triisopropyl chloride, three bulky isopropyl groups are pushed together due to sp3 angle of 109 degrees. Here 109.5 degrees is there, and this pushing together results a strain called B strain, back strain. In this B strain is there, that means back strain. Because of this one, what happens when this ionages, when the compound ionages, that means actually this is obtained from chloride only. So I'll attach chlorine here to this here. Now I will remove plus. So between carbon and chlorine, once the bond is separated, triisopropyl chloride will come, and the chlorine went automatically carbocation generates. Once the carbocation generated, what will happen? It will be looking like this. This is positive, and it is having an empty orbital perpendicular to the plane of that groups. Okay. Here we can write like this. Okay, here when this triisopropyl chloride ionages, what they're telling is angle expands from this 109 to 120. So what is the angle here is 120 degrees, and resulting the relief of the strain due to increase in space between alkyl groups. So here such kind of carbocation would resist addition of nucleophile, as it would result the crowding of bulky groups together. So here what we notice is stability of this carbocations is attributed to steric relief. So in substrates like triisopropyl chloride, we have observed this beautiful example. Because of this sp3 hybridization, In triisopropyl chloride, it is 109.5, 109 degrees. This 109 degrees has become 120 degrees because of this steric factor. So the steric factor is working. Steric relief observed in the case. In this case, we observed a steric relief. Okay. So this is the most important point we have noticed in the case of carbocation. Not only this one, we have discussed the things related to the carbocation examples. Even you have any kind of things are there. We're going to talk about that one. For example, if you take one more example. Here I am going to write one question to conclude this session. What is the question is, which of the carbocations is most stable? That means they are giving A like this. N side they are given a positive charge, and B they are given like this. It is there here, positive charge given. So which of the carbocations is more stable? Which of the carbocation is more stable? This is what they have asked a question. Here we have to go with the example A is the right answer, because it is a tertiary carbocation. This is a tertiary carbocation A, and also this is a allylic one, allylic carbocation. Because of this one, this kind of the answer we have to give. The next one we will see, that is another question we will see, that is pH, CHCl, CH3. This is A. Another one B they are giving, that is pH, CH2, CH2Cl. What is the question is, CCl bond is which one has CCl weak bond? Which one has CCl weak bond? Here in this, if you observe A structure A, we have a weak bond between carbon and chlorine. We can understand weak bond, because the carbon and chlorine will be separated out hydrolytically, And we end up with carbocation in this case. Carbocation, carbon with positive charge will come here. Over this once carbon and chlorine got separated out. And moreover, that is said to be a benzyl carbocation. So A will give benzyl carbocation that is more stable than the other one, B. So B, if CCl bond is separated out, we will get a carbon, sp3 carbon with the chlorine bond is there, and that carbocation formed is not strong, weaker, is a stronger one, because CCl bond in the B option is a stronger one than the A option. Okay, so benzyl carbocation will be easily formed. The bond between carbon and chlorine will be easily broken in the A option. So A is the right answer for this one. And what is the thing is, we will get benzyl carbocation in case of A. That's why we go with A. That is the answer for it. Okay. Okay. This session I have discussed about the reaction intermediates we have started, and we have discussed about carbocations in this session. In the next session, we'll discuss the other important intermediates. Until, thank you.